Hello everyone, I'm Grzegorz Dudek from Częstochowa University of Technology, Poland, and I'm going to talk about generating random parameters in feedforward neural networks with random hidden nodes, drawbacks of the standard method, and how to improve it. Single hidden layer feedforward neural networks with random hidden nodes have become popular in recent years due to their fast learning speed, good generalization performance, and ease of implementation. They don't use gradient descent method for learning. In randomized learning, weights and biases of the hidden nodes are selected at random from any interval -u, and stay fixed. The optimization problem becomes convex, and the output weights can be learned using a standard linear least squares method. The resulting neural network has a universal approximation capability. But how to select this interval and which distribution to use are open questions. Typically, the weights and biases are both selected from a uniform distribution over the fixed interval -1, 1. The sigmoids, which parameters are selected from this interval, are shown in the middle panel. They are combined linearly. The lower panel shows sigmoids multiplied by the output weights. The sum of these functions gives the fitted curve, red line in the upper panel. Note that in this case we get two flat sigmoids. Many of them have their inflection points outside of the input interval. The steepest fragments don't correspond to the steep fragments of the target function. As a result, they can't be combined to obtain the target function. Fitting improves when we optimize the interval. For the interval -10, 10, the sigmoids are steeper and are able to fit the target function. But note that many sigmoids have the steepest fragments outside the input interval, having their saturated parts in it. They don't build the fitted curve and are useless. From these simple examples, it can be concluded that to get a parsimonious flexible model, the sigmoids should be steep enough and the steepest fragments should be inside the input interval. Let's see how the inflection points, chi, are distributed when the weights and biases are selected from the uniform distribution over the interval -u, u. The probability that the inflection point is inside the input interval is only 1/4. This means that most sigmoids have the most useful, steepest fragments outside of this interval. To obtain an n-dimensional sigmoid with one of its inflection points inside the input hypercube, first, we generate weights A from the interval -u, u, and then we calculate the bias using the weights and the point x randomly selected from the input hypercube. As you can see in the figure, all sigmoids are inside the input interval. It should be noted that weight A translates nonlinearly into the slope angle of a sigmoid. Distribution of the slope angle alpha when weights are generated from different intervals are depicted in the figure. For narrow intervals, the distribution of alpha is similar to a uniform one. When the interval is extended, larger angles near the bounds are more probable than smaller ones. In such a case, there is a real threat of overfitting. To generate sigmoids with uniformly distributed slope angles, first we generate alpha from the interval alpha min alpha max, where the border angles are adjusted to the problem being solved. Having the angles, we calculate the weights and biases. And some results for 3 target functions. Each of them is 2, 5, or 10 dimensional. Lower figures show fitting errors for different number of nodes. PM alpha in all cases leads to the best results. For n equal to 2, it needs less nodes to get a lower error than PMU and SM. Interestingly, for higher dimensions, using too many nodes leads to an increase in the error for SM and PMU. This can be related to the overfitting caused by the steep nodes generated in the standard approach. In the same time, for PM alpha, where the node slope angles are distributed uniformly, a decrease in the error is observed. Similar results we can observe for other test functions. And now more details on the inflection points distribution. The sigmoid value at its inflection point chi is 0.5. From this equation we obtain inflection point as a ratio of the weight and bias. The distribution of the inflection point is a distribution of the ratio of two independent random variables having both the uniform distribution. In such a case, the probability density function of chi is as follows. Thus, only 1/4 sigmoids have their inflection points inside the input interval. Situation improves for the multivariable case when we consider n-dimensional sigmoids. For n equal to 2, almost 46% of sigmoids have their inflection points in the input rectangle. This percentage increases to more than 90% for n larger than 7. To obtain an n-dimensional sigmoid with one of its inflection points chi inside the input hypercube H, first we select randomly weights from the symmetrical interval, which border value is adjusted to the target function. Then we set the sigmoid in such a way that chi is at some point x asterisk from H. From this equation we obtain equation for bias. Thus the bias is dependent on the weights selected first. Point x asterisk can be selected as a randomly chosen point from H. This method is suitable when the input points are evenly distributed in H. This can be some randomly selected trining point. This method distributes the sigmoids according to the data density, avoiding empty regions. And this can be a prototype of the trining point cluster. This method groups the trining points into m equal to a number of nodes clusters. For each sigmoid, a different prototype is taken as x asterisk. To obtain distribution of the sigmoid slope angles depending on the interval for A, let's analyze sigmoid S, which has its inflection point chi in x equal to 0. In such a case, B is also 0. A derivative of S in x equal to 0 is equal to the tangent of its slope angle alpha in chi. From this equation we obtain equation for alpha. This relationship is depicted in the figure as well as the PDF of alpha when weights A are generated from different intervals. Note that the relationship between A and alpha is highly nonlinear. Interval -1, 1 for A corresponds to the interval -14, 14 for alpha, so only flat sigmoids are obtainable in such a case. For A from the interval -10, 10, we obtain alpha from the interval -68, 68, and for alpha from -100, 100, we obtain alpha from the interval -87, 87. For narrow intervals for A, such as -1, 1, the distribution of alpha is similar to a uniform one. When the interval for A is extended, the shape of PDF of alpha changes. Larger angles near the bounds are more probable than smaller ones. When A is from the interval -100, 100, more than 77% of sigmoids are inclined at an angle greater than 80%, so they are very steep. In such a case, there is a threat of overfitting. To generate sigmoids with uniformly distributed slope angles, first we generate alpha individually for them. The border angles alpha min and alpha max can both be adjusted to the target function. For highly nonlinear target functions with strong fluctuations, only alpha min can be adjusted, keeping alpha max as 90 degrees. Having the angles, we calculate the weights from this equation. For the multivariable case, we generate all n weights in this way, independently for each of m sigmoids. This ensures random slopes between alpha min and alpha max for the multidimensional sigmoids in each of n directions. The proposed methods of generating random parameters of the hidden nodes are summarized in algorithm 1. In this algorithm, weights A can be generated randomly or optionally to ensure uniform distribution of the sigmoid slope angles. They can be determined based on the slope angles generated randomly. The bounds U, alpha min, and alpha max should be selected in cross-validation. The inputs are number of hidden nodes m, number of inputs n, bounds for weights or optionally bounds for slope angles, and a set of m points x asterisk. The outputs are weights, matrix of weights A and vector of biases B. In these two loops, for each node and for each dimension, we select randomly individual weights or optional individual slope angles, and then we calculate the weights. Finally, we calculate the bias for each hidden node. Conclusions. A drawback of the standard method is that many sigmoids have the most nonlinear fragments outside of the input hypercube, especially for low-dimensional cases, so they can't be used for modeling the target function fluctuations. Moreover, it is difficult to adjust the optimal values for weights and biases when the standard method selects these both parameters from the same interval. In this work, we propose methods of generating random parameters which ensure that all the sigmoids have the steepest fragments inside the input hypercube. In addition, we show how to determine the weights to ensure the sigmoids have uniformly distributed slope angles. This prevents overfitting, which can happen when weights are generated in a standard way, especially for highly nonlinear target functions. The proposed methods treat weights and biases separately due to their different functions. The weights are determined first, and then biases are determined on the basis of weights and data distribution. The basic conclusions of this work can serve as general guidelines for designing feedforward neural networks with random hidden nodes for regression. Thank you very much for your attention.